Swayam Prabha. Digital India. Educated India.
Hello friends, this is Professor Ravin Zugade from Department of Chemistry, Rashtrasant Tukadoji Maharaj, Nagpur University, Nagpur. And we are discussing about the BSc Semester 1 curriculum as per the BSc Honours Chemistry course. And in this particular module, we are discussing about the chemical bonding. This is the second lecture on chemical bonding. In first lecture, we have discussed some part of ionic bonding. And now this is the second part of the same topic. The lecture has been prepared under the academic expertise of Professor L.J. Paliwal from Department of Chemistry, RTM, Nagpur University. The outline of this particular module is ionic bonding, covalent bonding, theories of covalent bonding, metallic bonding, weak chemical forces, and oxidation and reduction. And in this topic, we are discussing about ionic bonding since last lecture. Now, continuing the same topic of ionic bonding in this lecture too. So let us see the next part of the lattice energy which we have discussed in the previous lecture. Now, we have discussed in the previous lecture that lattice energy is the energy released when exact number of gaseous cations and gaseous anions they combine to form 1 mole of solid ionic crystal, that is called as the lattice energy, generally expressed in terms of kilojoule per mole or kilocalorie per mole. Now, in order to determine it experimentally, actually theoretically if we see, the Na positive gaseous ions should combine with Cl negative gaseous ions to give solid ionic crystal of NaCl having composition 1 mole, and the amount of energy released will be called as the lattice energy. But it is impossible to determine this lattice energy experimentally due to the fact that it is not possible to have Na positive ions in the gaseous state and Cl negative ions in the gaseous state, because we know that the ions do not exist in gaseous state or they cannot be isolated in the gaseous state. So it is not possible to experimentally determine the value of U. So U have to be determined indirectly, and hence this indirect determination is based on a cycle called as the Born-Haber cycle. And we will see what are the different steps which are involved in the Born-Haber cycle to determine the value of lattice energy on the basis of various other energies which are involved in the formation of this NaCl as an example of any ionic crystal. It can be any ionic crystal of Mx type where M is metal and X is the non-metal part. We know that all the ionic crystals or ionic compounds are generally formed by one metallic part and one non-metallic part, one electropositive species and one electronegative species. So as an example, we are considering NaCl formation, and with that the amount of U is to be determined experimentally but in an indirect manner. So now let us see what are the various steps. So they are based on Hess's law of constant heat summation. This Born-Haber cycle works. What this law says? The law says that the heat change accompanying a chemical reaction is same even if the reaction takes place in one step or number of steps. Let us try to understand the concept behind this. This law says that the energy change, heat change is a common word for energy change in thermodynamics. So whatever is the amount of energy change or the heat change associated with any chemical reaction will be equal even if the reaction takes place in one step or two step or three step. The same reaction taking place in number of steps or a single step, the overall energy change associated with that particular reaction will be equal. That is, formation of ionic compound can be expressed in multiple steps, and from that we can calculate the lattice energy indirectly. We will see with an example of NaCl. So if we consider the example of formation of solid NaCl from solid sodium and gaseous chlorine. Let us try to understand this, because the natural form of sodium is solid and natural form of chlorine is Cl2 gas. So the formation of NaCl will be from solid Na and gaseous chlorine. Okay, now let us see what are the steps which are normally involved in the formation of NaCl. If we write the expression of formation of NaCl, the formation of NaCl can be shown as sodium solid plus half Cl2 gas will give you NaCl solid, 1 mole of solid ionic crystal from the constituent elements in their standard states. What is the standard state of sodium? Is solid. Standard state of chlorine is gas. And whenever this type of reaction is written, the energy change or the enthalpy change associated with this process is called as enthalpy of formation. So whatever is the amount of energy released, that is called as enthalpy of formation of NaCl. This enthalpy of formation is defined as the amount of energy absorbed or evolved when 1 mole of a compound is formed from its constituent elements in their standard states. So standard state of sodium is solid, standard state of chlorine is Cl2 gas. So whatever is the delta H, it will be called as enthalpy of formation, represented by symbol delta HF. Now this can be experimentally determined because sodium exists naturally in the solid state, chlorine exists naturally in the gaseous state, and NaCl can be formed from them, and whatever is the amount of energy released, that will be called as enthalpy of formation, experimentally determinable quantity. Now the same reaction can be expressed in terms of multiple steps. The first step is conversion of metallic sodium into gaseous sodium atoms. So this process can be shown as solid sodium absorbing some amount of energy getting converted into gaseous sodium atoms. Now conversion of solid into gas directly without going through liquid state is called as sublimation, and hence whatever is the amount of energy absorbed in this process is called as delta H of sublimation or enthalpy of sublimation of sodium. So this is enthalpy of sublimation is available in the literature. The value can be obtained from the literature itself. Second step, similar to sodium, chlorine also undergoes dissociation. Chlorine naturally exists as Cl2 gas in the molecular state, and if we supply amount of energy to this gaseous molecule, it gets converted into gaseous atoms. Now we will be requiring only one Cl atom for the formation of one NaCl molecule. So we are taking into consideration only half Cl2 gas, requiring half of the energy which is called as the dissociation energy or enthalpy of dissociation of Cl2 molecule. So half of the energy will be required to get 1 mole of chlorine in the gaseous form. So first step, sodium getting converted into Na gaseous atoms. Similarly, second step is conversion of Cl2 molecule into Cl gaseous atoms. So we are now having the free atoms of sodium in the gaseous state, free atoms of chlorine in the gaseous state. In the third step, let us convert the gaseous sodium atoms into sodium cations. For this, we will have to remove electron from the outermost shell of sodium atom, and the amount of energy required to remove the outermost electron from isolated gaseous atom is called as ionization enthalpy. So whatever ionization enthalpy we supply, called as ionization enthalpy or sometimes also as ionization potential. So that energy is to be supplied to sodium to convert it into gaseous cation. Similarly, we have to convert the chlorine atoms into chlorine anions or chloride ions, and for this we will have to add one electron to the Cl gaseous atoms. And during addition of the electron, some amount of energy is released, and this energy is called as electron affinity or electron gain enthalpy. Now we are having sodium in the gaseous state getting converted into Na positive, Cl in the gaseous state getting converted to Cl negative. Now we are having Na positive in the gaseous state and Cl negative in the gaseous state. Let us combine them together, and combining them to give solid ionic crystal, and whatever is the amount of energy released when exact number of gaseous cations and gaseous anions combine to form 1 mole of solid ionic crystal, the amount of energy is called as lattice energy. Now if we observe all these 5 steps clearly, it starts from sodium in the solid state and Cl2 in the gaseous state, combining and ultimately leading to formation of 1 mole of solid ionic NaCl. It means that these 5 steps is a combination. On combination, these 5 steps will lead to the first reaction. That is, according to Hess's law of constant heat summation, the delta HF or formation of enthalpy of formation of NaCl will be equal to sum of all these 5 energies according to Hess's law of constant heat summation, which says that reaction may take place in one step like this, or it may take place in number of steps like this. The total amount of energy which is involved in the process, or the energetics which is involved in the process, will not change. It will remain same. So we can say that delta HF of this will be equal to sum of all these values. Now the question is, where is the cycle now? Now we can show the same process in a cyclic manner. Let us start with solid sodium and half Cl2 in the gaseous state. So they are their standard states. Now what we are doing is we are supplying energy to sodium atoms, which is equal to enthalpy of sublimation of Na getting converted into gaseous sodium, keeping chlorine as it is, half Cl2 in the same form without any change. So this is the amount of energy which we have to supply. So on this axis we are having energy. So when we supply energy, the energy of system will increase and it will raise to higher value. So now the energy of this system is higher than the energy of the previous system, because we have supplied an energy equal to enthalpy of sublimation of sodium. Now what we do is we supply some more energy which is equal to ionization enthalpy of sodium, convert sodium gaseous atoms into sodium gaseous ions, and this is by release of the outermost electron, and for removal of that electron the amount of energy required will be ionization enthalpy. In the third step, we convert this chlorine gaseous molecules and dissociate them to gaseous atoms. So that is called as the enthalpy of dissociation. And since there are half mole of Cl2 required to give 1 atom of chlorine or 1 mole of chlorine, what we will be requiring will be the half of the enthalpy of dissociation. Again, this is the amount of energy which is absorbed by the system, and as a result the energy of the system will further raise up. So these are the steps where we are supplying the energy. After this we want to add 1 electron to this chlorine gaseous atom. Now when we add electron to this, amount of energy released will be called as electron affinity or electron gain enthalpy, and this energy released leads to formation of this Cl negative in the gaseous state. Now the energy of this system has lowered down as compared to the energy of the previous system, and from here we have Na positive in the gaseous state plus Cl negative in the gaseous state theoretically, and combining them together with the release of energy called as the lattice energy, we will get 1 mole of solid ionic crystal of NaCl. So ultimately we have started from the standard states of sodium and chlorine, and we have reached to the standard state of NaCl solid. Overall, if we see the reaction is nothing but conversion of Na solid plus half Cl2 gas giving NaCl solid. This is the energy, overall energy change is given by delta HF. This is what is called as Born-Haber cycle. So if we see this expression, this is a single step process and this is a multiple step process. The net energy change is just between these two, and that is called as the delta HF, or enthalpy of formation of the NaCl solid. This is how the Born-Haber cycle works, or Born-Haber cycle can be expressed. Now this can be used to calculate this enthalpy, or what we call it as the lattice energy of NaCl. This can be done because delta HF can be experimentally determined. Delta H of sublimation is known from the literature. Ionization enthalpy of sodium known from the literature. Delta HD, the dissociation energy or dissociation enthalpy of Cl2 gas, is known from the literature. This EA, electron affinity of chlorine, is known from the literature. So since all the other things are known from the literature, we can calculate this lattice energy or lattice enthalpy by calculation using this Born-Haber cycle. We will see actually mathematically how it can be calculated. Let us see. This delta HF, the overall enthalpy of formation, is now equal to delta H of sublimation of sodium plus half delta H of dissociation of Cl2 gas plus ionization enthalpy of sodium plus electron affinity of chlorine plus lattice enthalpy U. This is a mathematical expression. Now putting all the values of delta HS, delta HD, ionization enthalpy, electron affinity and delta H of formation, we can calculate the value of U as U equal to minus 758.7 kilojoule per mole for NaCl solid. This is how the Born-Haber cycle works to calculate the lattice enthalpy or lattice energy of NaCl. Now this can be applied to any of the crystal like KCl, CaCl2, all the ionic crystals. You can apply this particular type of Born-Haber cycle, which is actually an extension of Hess's law of constant heat summation. Coming to another aspect of solvation of ions and solvation energy or solvation enthalpy. Now we know that the interaction of solvent molecules with the solute ions, that is called as solvation. Whenever you put any ionic compound into a solvent, there is an interaction between the solute ions and the solvent molecules, and that particular process is called as solvation of the ions. And if the solvent is water, we use the word hydration because we use the word hydra for water. Such interaction takes place mainly in the polar solvent because we are talking about ion interacting with the solvent molecules. And if water is there, then we know that water is a polar solvent because of the high electronegativity difference between oxygen and hydrogen. And so we can represent the water molecule like this. We know that oxygen is more electronegative than hydrogen. As a result, it will pull the bonded electron pair towards itself. Hence, hydrogen will acquire partial positive charge on both the sides. So both hydrogen atoms acquiring partial positive charges and oxygen atom acquiring partial negative charge. And because of this, this water molecule behaves as a dipole. Hence, solvation is actually the interaction between this dipole and the solute ions which are dissolved in water as a solvent. Let us take an example. For example, if we have NaCl dissolved in water, when you put NaCl solid into water, let us see what are the various phenomena which take place. First thing which takes place is NaCl getting dissociated to form sodium cations and chloride anions. So NaCl solid getting converted to Na positive ions and Cl negative ions. In the second step, each sodium ion will be surrounded by large number of water molecules with the oxygen atom facing the Na positive ion. Why oxygen atom facing Na positive ion? Because oxygen bears partial negative charge and Na is having positive charge. So there will be interaction between the oxygen terminal of water molecule and Na positive ion. So what we can show is Na positive is getting hydrated by large number of water molecules. We do not know what is the value of this X. So that's why we have put an unknown number. It can be arbitrary number X. So some molecules of water will definitely coordinate with Na positive, and this particular species we call as a hydrated Na ion or hydrated Na positive ion. The overall charge on the ion will be positive because Na is positively charged and H2O is neutral. So how many number of water molecules are there? Whatever is the number of water molecules, the overall charge on this particular species will be +1. Similarly, each chloride ion will be associated with water molecules with the hydrogen atoms facing the chloride ions. So we are having some Y number of water molecules coordinating with the chloride ions with hydrogen terminal, and both the things can be shown like this. Due to interaction between the water molecules and the ions, we know the interaction is a attractive interaction, and whenever there is attractive force, the energy is released, and that energy is called as solvation energy. If the molecule is water, it will be called as a hydration energy or hydration enthalpy. The situation can be shown something like this. So we are having Na positive ion getting surrounded by a large number of water molecules with the oxygen terminal facing the Na positive ion. So situation will be something like this. Exactly opposite will be the situation in case of chloride ion. Now in chloride ion, the facing of chloride ion will be towards the H terminal of water molecule. The reason is H is having delta positive charge, whereas Cl is having negative charge. So this will be facing towards chloride ion, and this is what we call as a hydration of Na positive ion. This is what we call as a hydration of chloride ion. And in both the cases, there are attractive forces between the ion and the solvent molecule. And because of these strong attractive forces, some energy is released, and that energy is called as the solvation energy, which acts as a driving force for dissociation of this Na positive and Cl negative ions away from each other. Now, whenever you have, suppose positive ion is there, which is associated with water molecules with the oxygen terminal facing the ion, positively charged ion. So there will be forces of attraction. Now this is called as the primary hydration sphere. If other solvent is there, it will be called as a primary solvation sphere. Whenever there is a formation of primary hydration sphere, definitely the outer portion of this will bear H with delta positive charges. Hence, there will be association of a secondary hydration sphere with the oxygen terminal facing this hydrogen terminal of the primary hydration sphere. So there will be electrostatic interaction between the hydrogen atoms of the primary hydration sphere and the oxygen terminal of the secondary hydration sphere. There can be third hydration sphere also around this, will be called as a tertiary hydration sphere. So number of hydration spheres will be there. The electrostatic interaction will be strongest between the ion and the primary hydration sphere, and it will go on weakening when we go from primary to secondary to tertiary hydration spheres. So this is how the sphere formation will take place, and when the ion will move along with its hydration sphere. As a result, the mobility of the ion is not only the property or inherent property of that ion, but it is the property of the entire hydration or solvation sphere which is associated with that ion. Now we can express the solvation energy also in terms of Born-Haber cycle. Suppose we have NaCl, which is a solid NaCl. If we dissociated it into gaseous Na positive and gaseous Cl negative, we will have to supply an energy which is equal to the lattice energy. And these gaseous ions undergoing solvation, the amount of energy which is released will be the solvation energy, getting converted into Na positive plus Cl negative in the hydrated manner, or Na positive aquated and Cl negative aquated. Similarly, if we dissolve this directly and we can express it in a single step process with the some energy released when Na positive and Cl negative undergoing hydration to give you hydrated Na positive and Cl negative ions, and during this the amount of energy which is released will be called as heat of solution or latent heat of solution, and this heat of solution will be equal to lattice energy plus solvation energy. So we can apply the Born-Haber cycle based on Hess's law of constant heat summation, that this L will be equal to U plus delta Hs positive plus delta Hs negative. So sum of all these three energies will be equal to this heat of solution. Now what are the factors which affect solvation energy? The first factor which governs solvation energy is the ionic potential. Now, what is this ionic potential? This ionic potential is defined as ratio of charge to the radius of the ion. So whatever is the charge on the ion divided by radius of that ion will be called as the ionic potential. More is the charge and smaller is the radius, more will be the ionic potential. And more is the ionic potential, there will be strong interaction between the ion and the solvent molecules. As a result, when there will be higher charge density or higher ionic potential, the solvation energy will definitely increase due to strong electrostatic forces of attraction. The hydration energy follows the order for certain ions. If we see Na positive, Mg2 positive and Al3 positive, we can see that the charge is continuously increasing, and since this charge is in the numerator, the charge to radius ratio will go on increasing, that is the ionic potential goes on increasing, and when ionic potential increases, the hydration energy or in general solvation energy goes on increasing. Similarly, if we consider the size of the ion, when we go from Li positive to Na positive to K positive to Rb positive to Cs positive, the size of the ion, since the extent of charge is only 1 positive, but the size is continuously increasing, and since the size is increasing, the hydration energy will go on decreasing from Li positive to Cs positive. Here when I am talking about the size, it is size of the inherent native ion. I am not talking about the size of the hydration sphere, but it is the size of the ion itself, because we are talking about the ionic potential of the ion. In general, we can say that smaller size and higher charge will lead to more attractive forces, and it will lead to higher amount of solvation energy, which is the energy released during solvation. We will take an example. If we see this, we are having a series of ions, Li positive, Na positive, K positive, Rb positive, Cs positive. The ionic radius continuously goes on increasing and hydration enthalpy goes on decreasing. This can be shown diagrammatically, like the size goes on increasing, the hydration enthalpy goes on decreasing, like this. Second example is the same one, Na positive, Mg2 positive, Al3 positive. The charge density goes on increasing with increasing charge, and as a result, with increasing charge density, the hydration enthalpy also goes on increasing. So this is direct proportion, whereas this is an inverse proportion between the two factors. The second factor which affects the solvation energy is on the solvent part. It is the dielectric constant of the solvent which also affects the solvation energy or solvation enthalpy. The dielectric constant is a measure of polarity of the solvent, and we know that more is the dielectric constant, more polar is the solvent, and higher is the polarity, higher will be the solvation, or for water it will be more or stronger will be the hydration. And as a result, polar solvents will quickly dissolve ionic solutes because it will lead to stronger electrostatic interaction leading to release of lot of energy. If we consider water as a solvent, the dielectric constant is about 80.1 at 20 degrees Celsius. When it comes to ethanol, it decreases to 25.3. When it goes to ammonia, it further decreases to 16.61, and in benzene it is only 2.28. This is a reason why the same NaCl which dissolves quickly in water does not dissolve in benzene at all, because the forces of attraction between water and the ions Na positive and Cl negative are much stronger due to very high dielectric constant of water. In other words, we can say that more is the dielectric constant of the solvent, more will be the polarity, and more stronger will be the interaction with the ions, leading to release of lot of energy, and that acts as a driving force for solvation of the ions by the solvent molecules. The third factor which affects solvation energy is the lattice energy. Now we know that there are two phenomena which are taking place. First factor is the separation of the ions from each other, and in order to separate the ions from each other, the amount of energy is to be supplied, that is called as the lattice energy. At the same time, when solvation takes place, energy is released, called as the solvation energy. Now lattice energy is the amount of energy which is to be supplied, and solvation energy is the amount of energy which is released. Hence, smaller is the lattice energy and higher is the solvation energy, more favorable will be the solvation, because solvation energy favors solvation while lattice energy opposes solvation. It makes the ions bound together very closely in the solid ionic crystal. Hence, there is an inverse relation between lattice energy and solvation energy. Now let us discuss the ionic crystal structures, because in the crystals the ions are arranged in a systematic manner, an extremely systematic manner, because we know that in the oppositely charged ions there are attractive forces, in the similarly charged ions there are repulsive forces. So in order to have a perfect structure or a stable structure, there has to be nullification of all the attractive and repulsive forces among them, so that a stable crystal is formed. In order to understand the crystal structure formation, it is necessary to understand certain terminology which is used while discussing the crystal structures in ionic compounds. The first term which normally we come across is the space lattice. The space lattice is the regular arrangement of the constituent particles of a crystalline solid in three-dimensional space. Whenever we are talking about ionic crystals, the particles are the ions, the cations and anions, and the regular arrangement of these in the 3D structure or 3D space, that is called as a space lattice. And in this space lattice, every particle, in this case every ion, is represented by a point, and that point is called as a lattice point. So second definition is of lattice point. So this lattice point is nothing but, while representing a space lattice, each particle is represented by a single point, and that point is called as a lattice point. This particle, for ionic crystal, this particle will be either cation or anion. In case of molecular crystals, these particles are molecules. The third definition is of unit cell. This unit cell is actually the building block of our total crystal lattice. This is defined as the smallest repeating unit in space lattice, which when repeated over and over produces the complete space lattice, that is called as a unit cell. So we can construct the entire crystal structure by repetition of the structure of unit cell. It is similar to a brick which is used in the construction of a building. We know that a wall is constructed out of the number of bricks. So in the similar manner, a crystal lattice can be prepared from large number of repeating units which we repeat over and over. We will get the entire crystal structure, that is called as a unit cell. And the fourth definition is of close packed structure. Now, this close packed structure is an arrangement in which maximum available space in the crystal is occupied so that there are minimum deficiencies, minimum voids, minimum spaces available. So this is called as a close packed structure. So these are the four important definitions which we normally come across whenever we discuss ionic crystal structure. So we can represent this as space lattice is a three-dimensional arrangement of all the particles, whereas each particle is represented by a point, and these points are called as the lattice points. And if we observe this structure carefully, a smallest unit which is repeating to get this particular structure will be called as a unit cell. This is the diagrammatic representation of the three definitions which we have discussed. Now, in ionic solid, the ions are packed together into repeating array, and that array is called as a crystal lattice. The concept of crystal packing assumes that the ions are hard spheres, even if they are not in actual practice, but in order to construct the entire crystal structure or crystal lattice, we have to assume that the ions are hard spheres. And the easiest way to picture such an array is to arrange one layer of spheres and then the second layer above it, the third layer above it, and so on. So we can pack the ions in various ways, and on the basis of that we can get different crystal packings. This can be done by putting the spheres in various layers, and the layers are arranged one above the other. The identical layers are shown by identical symbol, and different layers are shown by different symbols. The first type of close packing is the simple cubic packing. Let us see how this simple cubic packing is obtained. Consider a layer of spheres. So each of this is a sphere, maybe a particular ion or a particular particle. So these particles are placed in such a way that each of them will touch the adjacent ions externally. Okay, so this is first layer of the spheres. Now let us arrange another layer on this layer in such a way that every ion will be covered by another ion. Now this layer will be called as a type of layer. Second layer is placed on this layer in exactly same manner as that of the first layer A. So second layer is also of A type. Again, we will put the third layer on this, again of the A type, because they are exactly placed one above the other. So if we put the layers one above the other in this particular fashion, it leads to what is called as simple cubic packing as shown over here. Now we can see the bottom layer is the first layer. If we consider these four atoms at the bottom, they are there. The second layer will be here, exactly one above the other. Third layer will be just above it, and in this manner we will have stacking just one above the other, and this type of packing is called as simple cubic packing. And this can also be shown diagrammatically with this particular diagram, where this is what is called as the unit cell, consisting of various spheres contributing some part of each sphere into this particular unit cell. The radius of each sphere is denoted by R, whereas the length of the unit cell will be represented by symbol A. So we will be using these two terms throughout the incoming lecture. Okay, so this is how the simple cubic packing comes into existence. Now let us count the number of ions in the unit cell of simple cubic crystal, or what we normally call as cubic close packed structure. Now in this structure or simple cubic structure, we are having, or we can see 8 particles at the corners of the cube, but they do not contribute 100% each to the crystal. This can also be shown in this particular fashion, and we can see that every ion has got some fractional contribution into this particular unit cell. The remaining portions are present in the adjacent unit cell. Now if we observe this carefully, every ion has only 1/8 contribution in the unit cell in simple cubic crystal. So we can now say that in this structure the ions are placed at the corners of the cube, and there are 8 lattice points in the unit cell. One ion is present at each lattice point, which is present at the corner of the cube. This ion is shared by 8 unit cells, and hence contribution of each ion in the unit cell will be 1/8. And since there are 8 such ions present, every ion contributing 1/8 into the unit cell, so total contribution from all the ions will be equal to 8 into 1/8, which is equal to 1. So we can say that the crystal, which is a simple cubic crystal having a unit cell which is having just one particle or one ion present in the unit cell, even if it looks 8 particles contributing to it, but contribution of each of them will be just 1/8, and hence we can say that simple cubic crystal has one particle or one ion per unit cell. Now there is a terminology called as packing fraction and packing efficiency. Let us see how the packing fraction and packing efficiency work. This packing fraction or packing efficiency is the percentage of a particular crystal lattice or percentage of the unit cell that is occupied by the ions, because we can see, if you see this simple cubic crystal, some portion is occupied and some portion is vacant. The vacancy it leads to destabilization, and occupancy leads to stabilization and closer packing efficiency. So this packing efficiency can be calculated in terms of packing fraction or in terms of percentage packing fraction. We will see the total volume of a unit cell is equal to A cube. If we observe this carefully in the simple cubic crystal, each sphere is touching the every other sphere. Now if we observe this carefully, the length of the unit cell is A and radius of this sphere is R. Relation between these two is twice R will be equal to A, or A is equal to twice R, and the volume of this cube or entire cube or unit cell is equal to A cube, which is equal to twice R cube, which is equal to 8 into R cube. So that is the total volume. Out of that, the fraction which is occupied will be the volume of one particle, because we have just seen that in case of simple cubic crystal, the unit cell consists of only one ion. There are 8 ions contributing 1/8 each. So there is only one particle, and since there is only one ion or one particle having radius R, the volume of the sphere is 4/3 pi R cube. So this is occupied volume and this is total volume. The ratio of these two is called as packing fraction. If we take ratio of these two, it comes out to be 0.524. It means that the packing fraction in case of simple cubic structure is 0.524. If we express it in terms of percentage, it is called as packing efficiency, which comes out to be 52.4%. What is the meaning of this? The meaning of this is that in this unit cell, 52.4% volume is occupied, while the remaining volume, which is 47.6%, is vacant, which is present in the form of what is called as a void, and that void is present in the center of this cube, and that is what we call it as a body center. So the center of the body of the cube. So that is a large volume, which is about 47.6%. This is how we can calculate packing efficiency and packing fraction for each of the crystal systems. Coming to second crystal system, that is a body centered cubic packing. Now let us start in the similar manner as that we have started in case of the simple cubic structure. First, we have an array of various spheres arranged in a systematic manner like this. Now, while putting the second layer, instead of putting the second layer exactly on the same ions or same particles, we place it in a different manner. So now this layer is A layer, and we are putting the second layer on the voids which are present in between the various spheres in the A layer. So this new layer is at different position, and so this can be represented as a B layer. So now you have a layer, then B layer, where all the voids are occupied by the new particles, forming another type of layer called as the B layer. And again we put a C layer above this, but since the third layer is exactly as of the A particle, it will be again called as a layer. So in case of body centered cubic packing, the stacking or the packing is of the order of the format A, B, A, B, A, B, and so on. In case of simple cubic crystal, the packing is A type. Here the packing is AB type. When we observe this particular diagram in a 3D picture, it looks something like this. So these are the bottom particles. This is the particle which is placed on the void, and again the next layer exactly above the first one. So this is A layer, this is B, and the top layer is again A. So it is a AB type of stacking. It can be shown something like this, and since there is one particle at the center of the cube, this is called as body centered cubic type of packing. This is how the packing takes place in BCC structure. Now let us count the number of ions in the BCC crystal. If we observe this diagram carefully, we will find that there are 8 particles at the corners of the cube and 1 particle at the center of the cube. This can be represented diagrammatically in a 3D manner like this. This is what we call as the space lattice or the unit cell, and this is actually the 3D picture of this. Okay, now let us count. Now in this structure, ions are present at each corner of the cube and at the center of the cube. Each ion at the corner of the cube contributes 1/8, and since there are 8 such ions contributing 1/8 each, the total contribution is equal to 8 into 1/8 will be equal to 1. So contribution by the corner particles will be total 1, and there is only one particle at the center which is entirely present in the unit cell itself. It is not present in any other, or its part is not present in any other part or any other unit cell. So its 100% contribution is in the same unit cell, and so the total contribution will be 1 from the corner particles and 1 from the center particle. So the total contribution in the unit cell is equal to 2. So we can say that in BCC crystal or in body centered cubic crystal, there are 2 particles per unit cell. Now let us calculate the packing fraction and packing efficiency in body centered cubic crystal. This can be shown like this. Now it's not that straightforward as that of the simple cubic, because the particles which are present at the edges or at the corners of the cube, they are not touching each other. There is a gap between them. So there is no relation like A is equal to twice R. The length is A, but this A is not equal to twice R. So we construct a triangle like this, where this is the edge length, this is the diagonal of the base, and this is exactly diagonal of the entire cube, opposite corners joined together. Now mathematically, if we call this as A, then this particular part will be A. So all the edges will be A because it is a cubic structure. If this is A and this is A, then according to Pythagoras theorem, we have this as A and this as A. So Pythagoras theorem can be applied to this bottom diagonal, and bottom diagonal will be root 2A. Now this is root 2A and this is A, and these two are perpendicular to each other. So this edge will be equal to root 3A according to Pythagoras theorem. And since if you can see this, the central particle, which is a single particle, is touching externally to this corner particle as well as this corner particle. So this root 3A is now equal to this one radius over here, one radius on this side, and 2 radii, which is equal to diameter of the central sphere. So 4 radius is equal to this root 3A, which is the diagonal of the cube. So this is a relation between A and R. So now the relation is not as simple as the simple cubic crystal, but we have got the relation as root 3A is equal to 4R. Putting this value, so now from calculations we have A is equal to 4 by root 3 into R. So this is 4R. So A will be equal to 4R upon root 3. Then total volume of the unit cell will be A cube, which is equal to 4R by root 3 whole cube. And the occupied volume is the volume of two particles, that is 2 into 4 by 3 pi R cube. And hence the packing fraction will be 2 into 4 by 3 pi R cube, which is the occupied volume, divided by the total volume 4R upon root 3 whole cube. When we calculate it, it comes out to be 0.68. That is, the packing efficiency in case of body centered cubic crystal is 68%. So from 52% it has increased to 68%. It means that most of the volume is now occupied. Only 32% is present in the form of voids or in the form of the gaps or holes. Coming to the face centered cubic packing. Now in this packing, again we put the array of the first sphere layer in this particular fashion. Now you can see there is a fundamental difference. Each particle is now touching 6 other particles in the array. This is face centered cubic, and in this fashion, this is what we call as the array number or array A pattern. Now in the second layer, we put the particles on the half of the available voids. So out of the 6, we have put 3 over here, and 3 voids are vacant. So this is a layer B or B type layer. Then we put 3 more spheres on the remaining 3 parts. So this is a C type layer. It is not similar to A, it is not similar to B, but it is a different type of array, A, B, C. And above this C, we put one more array which is exactly matching with A. So the pattern or the stacking manner or stacking pattern will be A, B, C, and so on. And if we observe this carefully, it will look something like this. There is a hexagonal type of packing over here. Then there are 3 spheres over here, three spheres in the staggered manner over here, and again this and this will match with each other. So what we call A, B, C, again A, B, C pattern. This is what we call as a face-centered cubic packing. Now let us count the number of ions in face-centered cubic packing. It will look something like this. And since we can see that there are particles at the corners of the cube and one particle at the center of each face, hence it is called as face-centered cubic pattern. Now in this case, the corner particles will contribute 1/8 each, and we know that there are 8 such particles. So the contribution from the corner particles is total 8 into 1/8 will be equal to 1. Now there are particles at the center of each face. Now these facial particles have half portion inside this and half portion outside this unit cell. Hence we can say that contribution of each of these particles is 1/2 in the unit cell. And since there are 6 such particles, so 6 particles will contribute 1/2 into 6 will be equal to 3. So the total contribution from the facial particles is 3. Total contribution from the corner particle is 1. Hence the total number of particles in the unit cell is 1 plus 3 equal to 4. So we can say that there are 4 particles in the unit cell of face-centered cubic crystal. Now let us calculate the packing fraction and packing efficiency in face-centered cubic crystal. In 3D picture, we can show the FCC lattice unit cell in this particular manner. Now again you can see that this sphere and this sphere are not touching each other. Who are touching are this central sphere is touching each corner sphere. So we can use mathematics and geometrical understanding to calculate the packing efficiency. If we draw a triangle like this and the edge length is equal to A, this edge length is also A, and according to Pythagoras theorem, the diagonal length will now be equal to √2a. So since this is A, according to Pythagoras theorem, this will be √2a. And if we observe this carefully, we can see this √2a is equal to 4 times r. See, this entire length is divided into 3 components. First component is the radius of this sphere, second component is radius of this sphere, and third component is the diameter of the central sphere. This diameter is equal to twice r. So this is r plus twice r plus 1r is equal to 4r. Now mathematically, so you have A is equal to, calculating from this √2a is equal to 4r, A will be equal to 4r by √2. So 4r by √2, that is equal to 2√2 into r. So this is the edge length. So from the total volume of the unit cell will be equal to A cube, and this A cube is equal to 2√2 r cube, and this 2√2 r cube will be, out of that, since there are 4 particles in the unit cell, 4 particles will occupy a volume equal to 4 into 4 by 3 pi r cube, that is equal to since the packing fraction will come out to be 4 into 4 by 3 pi r cube divided by the total volume of the sphere 2√2 r whole cube, that comes out to be 0.74, indicating that the packing efficiency is 74%. The meaning of this 74% is that out of the total volume, 74% of the volume is occupied by the particles, while only 26% of the volume is remaining as unoccupied or in the form of voids. The last type of packing is the hexagonal close packed structure. Now in hexagonal close packed structure, the first array is similar to the previous one in case of the face centered cubic, but this is what is called as the A type. The second array is again similar to the face centered cubic, B type, but the third array is again of A type. So all of them are similar to A. So in case of hexagonal close packing, the stacking pattern is A, B, A, B, A, B and so on. It looks something like this. It differs from the face centered cubic structure. The packing efficiency, if we calculate in the similar manner for HCP lattice unit cell, is 74%, similar to the face centered cubic structure. Let us see a simple example of NaCl crystal structure. How NaCl looks like. It is having alternate arrangement of Na positive and Cl negative ions in the face centered cubic manner. So if we see this Na positive ions shown by the black spots, this is actually the Na positive ions are occupying corners of the cube and center of each face. So this is a FCC pattern of Na positive ions. If we see Cl negative ions in this particular diagram, it does not show exactly FCC pattern, but if we extend this to one more component, we can see that now the Cl negative ions, which are shown by the white circles or white spheres, they are also having the face centered cubic type of pattern. So we can say that the crystal structure of NaCl is actually a combination of two face centered cubic structures of Na positive and Cl negative ions respectively, which are fused together, and it leads to formation of crystal structure of NaCl. This is all about in this particular lecture, and this is all about the ionic type of bonding. Here the first component of chemical bonding, that is ionic bonding, is completed. We will continue with the chemical bonding topic in the next lecture number 3, and we will continue with the discussion on covalent type of bonding and other types of bonding in the subsequent classes. Thank you very much.